Alrighty, testing. For those curious, today I am drinking Chemex coffee. Alright, today we're going to be looking at ONNX. This is a open source project coming out of Microsoft Research that is basically used to run machine learning models on a variety of platforms. So why are we looking at this? So in the past couple videos, we've been looking at Unreal Engine versus Unity, these game engines, and one of the things we eventually want to do in these game engines is use machine learning, right? And in order to use machine learning, we're going to have to be able to export something like a PyTorch or a TensorFlow model, and then be able to run it on the hardware, hopefully on the hardware of the MetaQuest Pro. But so yeah, the tool to do that is called ONNX. Yep. So designed to accelerate variety of frameworks, operating systems, hardware platforms, etc. Parses through your model to identify optimization routines and so on. Training acceleration is not something we'll be really using it for, though. Using a single set of inference APIs, that's really the important one here. Full backwards compatibility. All ONNX and NX models can be inferenced. Yeah, and then they have all the APIs. They have C#, right, which you would use for Unity, C++, which is what you would use for Unreal, C, Python, and Java. Support for Linux, Windows, and Mac. Yeah, so all the languages, all the operating systems. Continuous community innovation. Blah, blah, blah. Here's a GitHub link. Let's see what they got. I think we already have this open. ONNX runtime, over 7,000 stars. Updates as early as yesterday. If we look at the commits here, a lot of people pushing. Let's look at the insights and then look at the contributors, see what that looks like. This is part of the Microsoft GitHub organization here. Open source projects, right? They have VS Code, Terminal, so on. I didn't realize VS Code had an actual repo. Let's go ahead and star that. Alright, still loading the contributors on the ONNX GitHub page. ONNX runtime abstracts custom accelerators. To this, partitions the ONNX model graph into subgraphs that align with available custom accelerators. When operators are not supported by custom accelerators or runtime, ONNX runtime provides a default runtime that is used as the fallback execution. Yeah, so you could think of this like shitty open source Microsoft CUDA. How about that? Okay, there's another page here on the ONNX website, and specifically we're going to use PyTorch as our machine learning framework. Low-key, I think PyTorch has beat TensorFlow. Okay, real quick here, back to the contributions or contributors for the ONNX repo. This is exactly what we want to see. This is a lot of activity. You have a variety of people here that are continuing to contribute. SNN, Scott McKay, Ed Chen. You have, yeah, this is exactly what we want. Look at all this activity. Look at all these people contributing. And they're not just contributing like this. You don't want to see this, right? Someone who started contributing a lot and then stopped. because that tells you that something might be dead, right? This project might be dead. This person left this project. You want to see people like Penghua here, where they've been contributing for a long time, and they contribute frequently, and they contribute all the way to the current date. So this is looking very good to me in terms of support and community. Okay, yeah, but basically PyTorch plus ONNX is what we're going to be trying to do this morning. So deploy anywhere, run PyTorch models on cloud, desktop, mobile, IoT, and even in the browser. Accelerate PyTorch models to improve, and blah, blah, blah. Okay. PyTorch includes support for ONNX through the ONNX torch.onnx APIs. Okay, so it looks like you can just do something as simple as this, import Torch, and then Torch already has the module in it. Let's click on this. We're like trying to get to a tutorial kind of point. Python not required. Yeah, and this is really what we're using this for. Deploying PyTorch models to many production environments, especially Android and iOS mobile devices. ONNX runtime is designed for production and provides APIs in C, C++, and so on. So we're going to be trying to deploy this via C++ to Android device, which I'm pretty sure is what the Quest Pro is. Inference with ONNX. Why don't we try to install this first? Okay. So let's go ahead and make a new pyenv. So I don't remember what that is, so let's grep pyenv. Okay, so pyenv virtual env. Let's go ahead and call this ONNX. Okay, then let's look at what exactly we want to do. Pyenv activate. Okay. Pyenv activate ONNX. Okay, so now we're inside our ONNX environment. And we are going to go ahead and install ONNX runtime. And do we want the GPU one? Let's do the non-GPU one, because there is no GPU in the MetaQuest Pro, and really that's what we want to see. Okay, so here they have the modules that are specific to other learning frameworks, sklearn, TensorFlow, but we're just going to want Torch, so let's pip install Torch here. It's also, I realize this is not great for you guys because you guys can't see the bottom of this terminal. So let's pip install upgrade pip just because it's complaining. It's in that nice shiny color. What about if I just had this like this? Would that be easier? Or what if I flip these? Yeah, let's flip these. Let's put this over here. And then let's put this over here. Okay. So let's open up a Python interpreter here and let's import Torch. And I think, what was the example that they had here? Torch.onnx.export. Let's see if that function exists. Torch.onnx.export, and then, I don't know, maybe we'll do something like that. Okay, so it does exist. Function export. Okay. So we do seem to have it. It is loaded. Let's see if, right here, we're on the installation instructions. Okay, you have the C versions, the web and mobile, NPM for you Java guys. iOS, install on Android. Okay. ORT training package. We don't really need that. That's for actually training. Okay, and then here you have kind of a table showing you all the different stuff. So let's go ahead, go to these tutorials here. Getting started in Python. A PyTorch computer vision model into an ONNX format. Okay, where is this model? Okay, we have to go on this PyTorch fundamentals here to see what this model is. Do they have the actual code here? Yeah. This is the model here. Okay, then load the model. Check model. Inference. TensorFlow computer vision. Scikit-learn computer vision. Okay. It's a different tutorial here. Text classification, which with the torch text library. You have the text classification model. Okay, it's basically going to be a whole PyTorch tutorial, to be honest. Okay, there's a couple different, I kind of like this. There's a bunch of different formats here. This is where we're ultimately building towards, by the way, the ONNX runtime for the actual thing. Okay. We have all the code for this. Do you guys want to do the NLP one or the vision? Let's do the NLP one just because I don't really do a ton of NLP. I'm not an NLP guy, so it'll look better. Let's put this in the better repo. let's make a directory called ONNX and then go in there. And then we'll let's touch a NLP tutorial dot, let's make this a notebook, and then let's go ahead and open VS Code there. Let's go ahead and open that, close the this default tab, and yeah, let's get started. So for this, I think let's make sure we're running in our ONNX Python environment that we created, or PyEnv. Then we'll import torch. Let's go ahead and say torch.onnx. Let's see if we can look at that. Look at that GitHub Copilot already ahead of us here. Let's see if there's something here, some kind of name, loader, version, something interesting we can output here. Annotations, producer version. Running kernels with requires IPy kernel. Okay, sure, install. I think basically what it wanted was it wanted the IPython notebook in this PyEnv. If we do pip freeze, this is all of them. I don't know how to get the specific PyEnv ones. Okay. So for this, we're also going to, let's get rid of this. Let's import torchtext.datasets, import ag from torchtext.datasets. Torch sets import ag news. Does this even exist? Yeah, it doesn't know what torch text is. How old is this article? Do they have it on GitHub? March 13th. Please install torch data. So you need to install torch data. How do you install this? Pip install torch data. Okay, let's see if now that runs. Python import torch text. Okay, still don't have torch text. Let's see if we just search the internet. No module torch text. Pip install torch text. Now let's try. All right, we got it. Let's get back to our torch data. Okay, so then we're gonna create a training iterator, and this is going to basically be the AG news dataset, whatever this is, and then splitting the train. So for example, here what they show is that you can say, give me the next item that comes out of this iterator, and this is what it is. So you have a tuple here that has some kind of sentence from I don't know, a news website or maybe a newspaper or something, and then whatever this first tuple is. I don't know what the 3 means. Okay. So this is the get iterator for training data. All right. Then we're going to prepare the data processing pipelines. Okay, from torch text data tills the tokenizer, and then from torch text vocab import build vocab from iterator. Okay. So those work. So our tokenizer is basically a way to turn these individual words and sentences and periods and stuff like that into what are called tokens, which are basically like little vectors. And these little vectors are a way to represent individual words and parts of words in a way that makes them better to train on, right? It's creating a manifold that a manifold of all human text, where words that are similar are close together, words that are different are far apart, words that have similar relationships, the vector between those words in that manifold is similar, right? So a famous example is like the difference between I don't know, like queen and king is the same as the difference between prince and princess, right? And these tokenizers are oh, wait up, no. I am incorrect there. The tokenization is just breaking it into little parts, the words into little parts. Then you convert those into a feature vector. So it looks like this entire tutorial is in GitHub Copilot, by the way. I'm just hitting tab here and it's automatically doing it. Okay, so now we're going to yield the tokens. You give it a iterator for blank in text, so it's actually getting rid of that first part of the tuple here, which we didn't really know what the fuck it was. And then it's yielding it. So this function is just going to return a tokenized text. What does this return here? Okay, we'll see. So then we have our vocabulary. It's going to build our vocabulary from the iterator. You're going to give it the function here that yields the tokens given a data iterator, and we're going to give it the training iterator that is the train split of the AG News data set. And specials equals unknown. So I suppose that when it doesn't know what a certain character is, maybe this like double backslash or this parentheses here or something weird like that, it'll just replace it with that. Not 100% sure if that's actually what's going to go on though. All right, set default index vocab unknown. Sure, let's see if that runs. Okay, seems to have run. Vocabulary block converts a list of tokens into integers. Okay. Foo. Hello. World. All right. So these are the integers which represent all the individual tokens, and it's a lot. 45,000. Foo is integer 45,000. Seems like a lot. I wonder what D is. D A it. V is the second one. It's not quite. Prepare the text processing pipeline with the tokenizer and the vocabulary, the text and label pipelines. Okay. So these are just pipeline. We can actually even get fancy here if you guys want. We can let's type this. Let's practice our Python here. From typing, import callable list tuple dict. Okay, then we come here, text pipeline. This is going to be a callable. I don't know what the fuck that was. Callable. And we're going to have a label pipeline, which is also going to be a callable. Our text pipeline is going to take some input X, it's going to tokenize it, and then it's going to turn it into integers for the vocabulary. And then the label pipeline is going to take some input X, which will be likely this integer, and then subtract 1. Which I guess is just to make 0 index it. Lookup table defined in the vocabulary, right? So vocabulary is the lookup table. Okay. Generate data and iterator. Okay, so kind of the next thing here is the data loader classes. Go utils and data. Device CPU. We could actually print. Let's print an F string here where we say GPU is available, and it's actually going to be no torch dot CUDA is available. Oh, not torch. GPU is available, true. So actually, technically, we can use the GPU there. Let's go ahead and say CUDA. And we have to wrap that in the torch.device call, which will return a device object rather than just the string. Okay. So works with a map style dataset that implements the get item and the length protocols and implements map from indices keys. It also works with an iterable dataset that with the shuffle argument of false. Yeah, so you can, these data loaders allow you to kind of define the batch and how the data is loaded at runtime when you're training. So shuffling, things like that. People extend these data loader classes in a variety of different ways. I'm sure ONNX has actually its own data loaders for its training, but we're not going to be using that. Okay, so GitHub Copilot just auto-completed this entire thing. Okay, what does this collate function do? Batch of data, process them according to the blah, blah, blah. declared as a top level function is available in each worker. Okay, so label list, text list offsets for label text in batch. Okay, so this is the label, I suppose. And then this is the text. So label list dot append label pipeline label. Process text equals text pipeline of text. So you're taking the text pipeline, you're putting it through this, or you're taking the text for each individual instance of the batch. You're tokenizing it, putting it through the vocab callable or vocab function, which will output an integer. It's going to create, right, it's going to basically take this, it's going to turn it into this, then you're going to make a tensor of int64, right, because there's big integers here. Then you're going to append the processed text to the text list, right, so you appended the label to the label list, the text to the text list. And offsets.append process text.size 0. Okay, so there's going to be different size text, so that's kind of what this last thing here is. Then you're going to create a tensor based on that offset, a tensor for the text, and a tensor for the label, and that's the full batch. Okay, so all we're really doing here in this collate function is we're basically taking what is normally just going to look like this, where you have a string and then an integer, and we're tokenizing it, converting it into a vector of integer 64s, and then for however many of these examples we have in our batch, we're putting them all into one big tensor and also having a offset so we know we can account for the different lengths. So then we're going to make this iterator for the bajillionth time here. And we're going to make a data loader object. Data loader, we're going to give it this train iterator. We're going to have a batch size of 8. Let's actually put the batch size up here. I like putting variables like this up at the top so you can always change them quite easily, or you always know where they are and you can change them and then run the entire notebook. We're going to be shuffling these so we can train on multiple epochs, and the batches are going to be different, and then we're going to give it this collate function. Okay, so now the next thing we're going to do here is we're going to define the model. Okay, so there's an embedding bag layer. The embedding bag is going to embed the words into, so we had our actual words, then we tokenize them, turn them into a vocabulary, where now they're just a bunch of integer indices, and then we're going to convert those integer indices into an embedding, right? And that embedding is then going to get fed into just a simple fully connected linear layer, and that linear layer is going to output the sentiment. I'm not like a sentiment guy, but is sentiment like 1 through 10? What exactly is the output here? Okay. So we're going to actually build the model. Class text classification model. This is expanding from the NN neural net module. Let's see here. Let's kind of double check this. So we have our init, which is going to run at the creation of this object. It has some vocabulary size, some embedding dimension, and the number of classes. So we're going to initialize this embedding bag network, and that needs the size of the vocabulary and the dimensionality of the final embedding that you want to use, and whether it's sparse. So interesting. I think this might reduce the overall computation or overall memory footprint of this embedding. It's actually sparse. If true, gradient with respect to the attribute weight matrix will be a sparse tensor. Okay. Sparse, self.sparse, sparse. Okay. Then we're going to create a single linear layer. We're going to call it FC. It's going to have the embedding dimensions, and then the final output is going to be the num class of it. Then for init weights, init range, we're going to initialize them with a uniform distribution from negative 0.5 to 0.5. FC weight data uniform, fully connected. This fully connected layer, the weights, we're going to initialize them to a uniform distribution of negative 0.5 to 0.5. And then finally, we're going to set the bias parts of the fully connected layer to 0. Then our forward pass here, this is what gets called when you actually perform inference, is going to take some text and some offsets, and then it's going to feed that through the embedding to create an embedding, right? So whatever comes out of this red part here. And then it's going to feed that through the fully connected network, right? This linear layer, self.fc, and then that'll be the actual output that we get. Let's go ahead and run that. Or not run, but create it. Okay, the AG news dataset has 4 labels, and therefore the number of classes is 4. Okay, so this is actually what the what that 3 was at the very beginning. So this is really just a supervised learning dataset where you have some text and then you have the class associated with that text, and there's only 4 possible classes here. Okay, so let's go ahead, and this is actually we're actually creating the model here. So let's actually just define these training and evaluation functions. Okay, I think we can actually put these down here. Let's not define that train iter anymore. Num class equals length of the set. Okay, set is basically like a list but unique. Label for label text in train iter. Okay, that is a very complicated way to get the, we could have just said 4, right? So this is going to go through everything inside the train iterator, right? The entire training data set. It's going to pull out the label, that first number in the tuple. It's going to make a set out of them, so only count the unique values, and then it's going to count the number of those. It's really heavy. Vocab size equals length of vocab. EM size equals 64. That's the embedding size. And the model, we're going to initialize an instance of this text classification model that we just defined, and we're going to give it the vocabulary embedding size and the num classes, and we're going to put it on our GPU. So actually, we should be able to watch-n 0.1 NVIDIA SMI. So here we're looking at this 732 megabytes used, and I think when we run this and we put this on the device, we should see that spike a little bit. Yep, there you go. All right. So we were at something like 700 megabytes, and now we're at something like 1,300 megabytes. So our model in total is something like 600 megs. All right. Define functions to train the model and evaluate results. Okay, so this is just our kind of train and testing loops here. We're going to have a train, call it train func. No, let's just call it train data loader. First thing we're going to do is we're going to call the model.train total accuracy and then a total count, because we're initializing these to 0, and then we're also going to define a log interval here of 200. Slightly shorter log interval than they have. Then we'll do start time. Okay. For index and then label text, or label text and offsets in enumerate data loader. So again, right, this data loader that we created earlier that we're going to be feeding in there, it has that collate batch function, right, and it outputs text offset label. So that's actually wrong. That's not the order that we have there. Where's our data loader? Text offsets. Text list. Oh, that's actually interesting. This is not the same as what GitHub Copilot put there. That is quite crazy that Copilot actually came up with something different, and we just kind of assumed that it was correct, but it's not the same. Okay, so label is the first, and we're going to put this on the device. Then the text is going to be the next one. Also, we're going to put this on the device, and the offsets we're going to put on the device. So it's label text offsets. Let's go back down, and we have for label text offset in enumerate data loader. Okay, we're going to 0 our optimizer. We haven't even initialized the optimizer yet. So yeah, we'll have to, I don't know if we pass that in or not, but 0 out the gradients on the optimizer. Then get the predicted label by feeding the text and the offsets into our model, and then we get the output, right, the predicted category. Then the loss is going to be whatever our criterion is, right, our loss function between the predicted label and the actual label. Then we're going to run that loss backwards. Torch clip grad norm. Okay, so we're gonna clip the gradients. Clip grad norm with an underscore at the end of it, whatever that does. What's the difference between clip grad norm with an underscore and clip grad norm without an underscore? Clip gradient norm of iterable parameters. This method is now deprecated in favor of clip grad norm underscore. Okay. So it just seems like they updated it and then they added the underscore to prevent that. All right, so then now that we've calculated the gradients and then clipped them so they're not quite as big, or at least they're limited to 0.1, we're going to take a step with our optimizer. And then we're going to basically calculate the, keep a running total of the accuracy by taking that predicted label. Argmax, right, it's going to be a one-hot, predicted label is going to be a one-hot, giving you the likelihood, right, the probability of each individual label being the true one, and we want to basically just take the one that's the highest, right, the category that has the highest score. Total count, sure, and then log. So every X amount of loss, or every log interval batch, go ahead and get the total time elapsed, and then print your standard crap here. Epoch, batches, accuracy. Let's just copy it from here. This code is generated. Like, epoch doesn't even exist here. Where are they getting epoch? There is no epoch. To know the epoch, you would have to know how many, you would basically divide the total size of the dataset by the batch size, and then you know how many batches there are in the dataset, and then once you run through that amount of batches, you would know that you've done an epoch. So let's just say batch number. I think that's what IDX is. Sorry. And why don't we actually calculate the so let's go through the entire train iterator here. Counter for label text in train iterator counter plus equals 1 print counter 1200. So to get the epoch, we are going to take the 1200, so dataset size, $120,000, we're going to say dataset size. Epoch is equal IDX plus 1 times batch size over dataset size. Wow, this GitHub Copilot is like changing the game here. I'm just living life in a GitHub Copilot world. Okay, then let's write our evaluate function of data loader. Right, it takes a data loader object, puts the model in evaluation mode, resets the total accuracy, total count with torch no grad. So again, you don't want to be calculating the gradient when you feed stuff in here. For IDX labels in enumerate data loader, so it's actually going to be the same one as this. Predicted label, model, text offsets, total accuracy, predicted label.argmax1 equals label. So if the predicted label with the highest logit is equal to the actual ground truth label, you sum all of those up across the batch. Total count is all of them, and then you total accuracy over total count. So the data loader that we give here should actually be different. This should be the test data. Okay, so let's actually define our optimizer up here. Optimizer equals, it seems like what they're going to be using here is torch.optim.sgd, standard gradient descent of model.parameters. And let's go ahead and have a learning rate LR. Epochs, LR, and batch size. Batch size, epoch, 10. Learning rate, we'll call it LR. Why not? We'll do 64. Okay, we can actually get rid of that, get rid of that, get rid of that. No, no. Okay, let's hit Shift Enter there, see if that works. Okay. Torch.utils.data.dataset. Let's import random split here. And from torch text .data .functional. Okay. Import to map style dataset. Okay. It's misspelled the from there. Okay, so we have our criterion. Torch.neuralnet.cross-entropy loss. I don't know why you want to device. I don't know what that does. The optimizer we already defined above. We're going to have a learning rate scheduler. So learning rate scheduler changes the learning rate as you go deeper into training, right? As you kind of move this little marble through this landscape, right? This hilly landscape, which is an analogy for gradient descent. But as you kind of go deeper and deeper in training, you want that little marble to take smaller and smaller steps because you're already in an area that's pretty good. So that's what you're really doing there. And gamma, GitHub says, Copilot says 0.9. This example says 0.1. So total accuracy, we're going to say none. Sure. Train, iter, and test iter is going to be this AG News data set that we keep bringing up here. Train data set, test data set is going to use this utility function here that converts it to a map style data set. Num train int. Okay, I don't exactly know what that means. I guess that's just only training on 95% of it. And then split train, split validation. We're going to random split the train data set, num set, length train data set minus num train. Okay, so that's this is going, the 95 is going to be our train validation split. Okay. And then we're going to create data loaders for these. All right, so we're going to have our train data loader, which has split train. Then the batch size from before, we're going to be shuffling it, and then we are going to use that collate function that we wrote earlier. And then let's also do our validation data set. No shuffling on that. Or it does seem like the validation and the test, they're shuffling here, but I don't think you actually want that. Not because it'll mess things up, but just it's unnecessary shuffling. Okay, and then let's actually do the training here. So for epoch in range, 1 epochs plus 1. Epoch start time equals time.time. We're going to train. Let's actually feed it the epoch so we don't have to like do what we were doing here and calculate the epoch. Train epoch criterion. Let's put these up here. Let's get rid of this. Okay, so we're giving the train our data loader and the epoch. We're getting the validation accuracy, and we're printing out what's going on. All right, so let's rerun that, and let's rerun this. See what happens. Name. Optimizer is not defined. Okay, so we need to rerun that, then rerun that, then rerun that. Expected all tensors to be on the same device, but found at least 2 devices, CUDA and CPU. Yeah, so I think let's rerun this entire thing. Clear outputs, restart, run all. Okay, GPU is available. Next, ran it. All right, and there we go. While this goes on, I am going to go take a bathroom break, so I'll be back in 5 minutes. Hopefully this is done training by the time we get back. All right, and we're back. And it seems like our little model has stopped training, so looks like the accuracy is higher. And our validation accuracy is actually good. So this is the train accuracy, so take that with a grain of salt because it overfits over time. Really, you want the validation accuracy. Cool, cool, cool. Accuracy. Okay, we're going to create a predict function here. Predict, given some kind of text, and our text pipeline, which we defined earlier. Torch no grad, of course. We don't want to calculate gradients for our just messing around. And we're going to put the text that goes into this prediction function into our text pipeline. We don't need it to go through the tokenizer, though. It just goes straight through the text pipeline. Then the model, you're going to give it the text torch.tensor0. I don't know why you need that. Oh, it's the offset. Okay. And feed that through the model, get the output, return the argmax plus dot item plus 1. Actually, I kind of want to see what what it thinks all of them are. Okay. So then let's say something, my text, we'll say, okay, so it has to be worlds, sports, business, or sci-tech. So let's say programmers everywhere rejoice. PyTorch PyTorch 420 is here, or 420.69, right? That's the magic Elon number. With this release, what is it autocomplete? We are excited to announce that PyTorch allows the latest CUDA and cuDNN. This release also includes a number of bug fixes and improvements. We have also added new Torch utils to help you identify checkout notes, blah, blah, blah. Okay, cool. Interesting that. Expected all tensors to be on the same device. Need to bring the model to the CPU or put this tensor in the GPU. Why don't we do this? To device. Wait up 1 second, I just sneezed all over the place. Alrighty. So this does not seem to work. I think what we're going to try to do instead here is we're going to put the model to the CPU. Only one element tensors can be converted to Python scalars. think you could do this. Data.numpy. Yeah. Okay. So our text, this like weird little Python, PyTorch text that was generated by GitHub Copilot, we fed it in, and this is the output. So, right, if one is world, sports, business, and tech, you see that these numbers are small, negative, and the one that's the highest is sci and tech. So it's really what it's predicting is sci and tech more than, and then the second highest would be world, third highest would be business, and finally the lowest score is sports. We can turn this into a probability with softmax, numpy softmax. Maybe we can do it in Torch. And then dot softmax. M of output. All right, so now we have something that looks a little bit more like a probability. 94% chance of sci tech, 0.008% chance of sports. Okay, cool. So now that we've completely forgotten what we were originally trying to do, which was to actually, this is what we were trying to do. We were trying to export the model into ONNX format and then inference with ORT. Okay. So now let's actually export the model here. So torch.onnx export model with ONNX. Export. Actually, I want to, let's do something here. Let's go on to, I'm going onto my phone and I'm searching for ONNX and I'm seeing if I can find ONNX runtime. I'm finding a YouTube video, right? This one right here, where they say it.
This episode of the AI Show, where Manoj Goswami, Principal Program Manager for AI Frameworks, tells us all about the ONNX runtime, what's new,
ONNX.
some amazing hardware.
Okay. It's just I just wanted to stop saying ONNX, right? They call it ONNX, so that's what I'm going to call it from now on. So torch.onnx. In this case, let's give ourselves a ton of space here. We're going to say export the model object. Okay. The next thing we need to provide here, actually, why don't we just go to this export function. Model args torch tuple or torch.tensor. The tuple should contain model inputs such that model star args is a valid invocation of the model. Okay. So when we call the model, we need to give it the text and then the offsets. So let's do that. It doesn't know what the text is. Okay, you need to create sample tensors for input. I guess it needs to know what the size is. So we'll say foo fake text. Then we'll feed that through our text pipeline, convert it into a torch tensor, and make a torch tensor for the offset. Okay. Where to save the model can be a file or a file-like object. So let's go ahead and put it here. If we go to our terminal, let's get that PWD. We'll copy that, put it there. And what are we going to call it? We're going to call it ag news model.onNX. I keep saying ONNX still. All right. Export parameters. Export param. So this store the train parameter weights inside the model file. Okay, I don't know why you would ever have that as false. Offset version. So the ONNX version to export the model to. How do we get the ONNX version? Print ONNX version. How to find version number of ONNX? Pip list find ONNX. One 1.13.1. I mean, that's not super helpful because this is version 10. GitHub Copilot's telling us version 11. All right, let's trust Copilot here. Do constant folding. Whether to execute constant folding for optimization. Sure. Okay, let's actually go see what the constant folding is here. Apply the constant folding optimization. Constant folding will replace some of the ops that have all constant inputs with pre-computed constant nodes. Okay, that seems like a good little optimization. Input names equals inputs and then offset. Okay, this is what you're going to call the inputs to the model. Output names is outputs. Let's call this something better. Text output names label. I kind of like that. It's a little bit more specific. Then we'll say dynamic axes. What is this? The variable length axes. Okay. And we're going to have the input. And this is going to be 0. And then whatever the batch size is. And then output is going to be 0, and then whatever the batch size is. Yes, install AutoPep 8 inside this so I can format. Okay. All right, so now if we run this, is not a valid input output name. Ah, yes, because we called it text and label. Okay, That's good. Let's open our this model, ag news model ONNX. Binary or uses. Let's just try to open it in a text editor. What does it look like? Okay. It has some metadata up here telling you the version of PyTorch. Then it's a bunch of basically weights or different, basically the architecture of the model. And this is much more complicated than just the fully connected head. So I think this is also the embedding model. So again, slices, constants, gathers, more slices, embedding dot weight, reducing mean, ONNX, and then this is probably the actual weights. Cool. If we actually go, so if you remember when we loaded this into our graphics card, it was like roughly 600 megs from what I recall. So on here, it's 24 megs. So kind of interesting. It's smaller. I wonder if that's compression going on or maybe what exactly is happening. But all right, let's get to it. The next step here, import ONNX. Okay. Import ONNX. ONNX model equals ONNX dot load, and we're going to load the ag news model we just created there. ONNX dot checker, check model. What does check model do? I don't know. ONNX check model. Okay, I guess this website just shows you check that the model is well formed. Okay. That's what it does. It checks the model. Who would have known? All right, create inference session with ort.inference. All right, so this little section here, no module named ONNX. Named ONNX. Okay, so that's a separate pip install ONNX. Okay. Application has cloned. Don't send. Sure. Okay. Oh, ONNX loads fine. The model looks good. What does this ONNX model object look like? It's a very nice string function, first of all. Tells you this is a PyTorch model produced with PyTorch 1.12.1. Has some output. Some text. And then the ONNX version is 11. It's actually... I wonder if this 0.12. So actually, let's do version 12. Okay. All right, then the next step is to create an inference session with ONNX runtime. And they want to call that ORT. Get NumPy in there as well. NumPy as NP. Then we're going to go ahead and make a inference session with that model. The outputs are going to be, we're going to take that inference session object. Let's actually go in there, see what that is. This is the main class used to run a model. You give it the model in ONNX format, session options. It would have been nice to know the type of those. Provider options, also unknown type. Providers, optional. Sequence of providers in order of decreasing precedence. Okay. The model will be inferred unless explicitly set. ORT will be inferred as ORT formats. All others are assumed to be ONNX formats. List of providers, so CUDA execution providers. Okay. We're going to give it text.numpy and then offsets.numpy. Or is it getting this text and offsets? It's up here. Let's write a sports one. The Google Gobbers won last night in a close game. The final score was 42-41. Let's do that. All right, so we feed that in there. We're giving the text. Let's put this up here. Let's make the input here. And results is equal to outputs of 0. Yeah, I don't really care about the argmax. I would rather see the whole thing. And print results. There you go, guys. Highest classification, or the class with the highest score, highest logit, was sports, which is what we thought. So here is the real test. We're gonna close out of this. Then we are going to reopen it. And we're going to go all the way down here to the bottom. We're not going to run any of these previous cells. We're just going to run this bottom cell here. And in that way, we're importing the model itself. So let's import torch. Text pipeline is not defined. Okay. So you need this. You need that. Yeah, because this is usually the problem, right? Is that now we need this text pipeline, but in order to get that text pipeline, we need all this extra crap. So we have the text pipeline, we have the vocab, which is required for the text pipeline, and we also need the tokenizer, which is this. So now look at all this different crap we need. Yield token is not defined. Train iter is not defined. Well, that's kind of worthless. You need the entire training data set in order to make the vocabulary in order to get the tokenizer. Ag news is not defined, so now you need to import ag news. Yeah, what's the usefulness of that, right? Shouldn't the tokenization be done or stored as part of the model? Callable is not defined. Let's get rid of this typing here. All right, there we go. So that's kind of annoying. We have all these extra dependencies just to turn our text input into something that the model can evaluate. But clear outputs of all cells. Let's also go into the gitignore virtual ems VS Code. Let's add another thing here and say saved models, and we'll say anything that's .ONNX. Don't add it. So whenever we do git add dot and git status here, it shouldn't have saved that .ONNX. Let's see vim.gitignore. It's star.onnx. Sorry. Star.onnx. Let's remove the ONNX agnews model. Okay, we'll remove that, and we're going to commit this the changes to the NLP tutorial here. Oh, let's close out of that. We will call this ONNX with PyTorch NLP. Go ahead and commit. All right, we're kind of getting to the end of this session here, but maybe we can start looking at what we can do kind of in the next session. So we looked at ONNX, we loaded a model, saved a model, we spent a bunch of time creating this model. But let's get rid of that. The ONNX runtime cross-platform inference. Okay. This is ultimately where we wanted to get to, is ONNX runtime and Unreal Engine. So this code sample shows you how to use the new NNI plugin for Unreal Engine 5, which implements ONNX runtime to allow you to add machine learning models into your project. Okay, so it gives you this urun model class that you can kind of inherit from, or you can extend it, I guess. They have here some examples, and they're using open source models from the ONNX Model Zoo. Okay, curious to see what that is. And then they're doing a style transfer. This requires Windows. We will see about that. Hit play. This is how to select a different model. Different models. ONNX models. ONNX Model Zoo. Over 5,000 stars. Contributions as only 10 days ago, so pretty good. You got everything here. You got MobileNet, ResNet, Inceptions, Shuffles, YOLO, all the way up to V4. Image manipulation, speech audio processing, language models, question answering models, autoencoders, text to image. Okay, ONNX you can deploy it to the kind of little shitty NVIDIA sticks that look like a little USB stick that's intended to run models on something like a Raspberry Pi. We have a bunch of Hugging Face models here. I wonder if they have a is this already filtered by ONNX? I wonder if they have stable diffusion. Yeah, but these aren't going to be ONNX. Okay. Cool. Well, that is that. I think the next thing we're going to do is we're going to try to do this Unreal Engine ONNX, but I think right now the stream is already getting too long, so we'll leave it at that. But